Welcome back. So we will do a very quick recap of where we were the last time. We introduced the concept of conditional probability. And by definition, if I know that B has happened, that's what this slash B means. If I tell you that B has happened, then you're actually limiting your consideration to a smaller sample space, if you like. And so the probability of A given B has happened is defined as this probability of them both happening divided by the probability of B happening. So we have that. All right. We looked at a bunch of examples. This thing can be generalized. See, if I bring this up here, you can see that the probability of A and B is the probability of A given B times the probability of B. This extends actually to any number of events. So if you have A1 and A2 and A3 all the way to AN, this is always true. This is possible to be decomposed as, okay, it's the probability of A1 happening times the probability of A2 happening given A1 has happened, and then the probability of A3 happening given both A1 and A2 have happened, and so on. I think I'll give the game away now and just say, if you have independence, you get that very famous thing, which I think most of you have seen in some context before. The probability of A1 and A2 and A3 all the way to N happening together is the probability of A1 times the probability of A2 times the probability of A3. When you have independence, nice things happen as well. Because when you have independence, it means whether you tell me this has happened or not has no bearing on whether A2 is happening. So the two are the same. So but we'll get there. So this is always true. There's no disclaimer, or this is only true when A1 and A2 are disjoint or whatever. This is always true. All right. So let's look at some examples for this one. Example 51. A study of texting and driving has found that 40% of all fatal auto accidents are attributed to texting drivers. 1% of all auto accidents are fatal. And drivers who text while driving are responsible for 20% of all accidents. Find the percentage of non-fatal accidents caused by drivers who don't text. Okay, so the first thing to do is write down the things that you know, all right? So in this case, we are told that 20% of drivers who text while driving are responsible for 20% of accidents. Okay, so what does this mean? This means if you text and drive, PT stands for drivers who text while driving having an accident. But you can text and cause an accident that's not fatal or fatal. So PT is 0.2, but PT is logically decomposed into, well, you did have an accident, but it was fatal or it wasn't. So that's 20%. So we have that. And then what else do we know? We know that we can decompose PT intersection F as PT given F and PF, and then PT given F prime PF prime. This is exactly what we just revised a minute ago. A conditional probability multiplied by this probability gives you back the intersection probability. Can anyone tell me why? Why do you think I'm writing this line here? Why do I choose to do this? Because basically, if I didn't do this, I'm kind of stuck. There's a whole bunch. I'm doing this because the information that's given to me is aligned this way. So do you see why PT/F is 40%? Because of all fatal accidents, if you know an accident is fatal, see, then it was the texting driver that's responsible for 40% of them. Among all fatal accidents, that's a conditional probability. See? So the wording is quite subtle. Among all fatal accidents, texting is responsible for 40%. That's why this is here. And then we know that the probability that an accident is fatal in the first place is only 1%. Automatically, is it clear to you, therefore, that this must be 0.99. Do you realize that this is what we actually want? We don't know this. This is certainly not 1 minus this, as I told you in class. If I condition on the event here, and this is prime, there's no such rule like that. This is what you want to find. So you write this statement down, and then you solve and do some simple algebra and manipulate stuff. That's okay. So you don't exactly want t given f prime. You actually officially the question wants you to do t prime given f prime. But that's easy because t given f prime and t prime given f prime are complementary. Right? So let's revisit the question. What did the question say? The question says, find the percentage of non-fatal accidents caused by drivers who don't text. See, the percentage of non-fatal accidents. So looking at the pool of non-fatal caused by non-texting. Okay? So this is a very important thing I want to bring across to the class. Use base rule to your advantage because it allows you to turn things around and state things in terms of conditional probabilities that are given. All right, it's an important skill to have. Okay, I want you to try this one. In a certain state, an individual may only attempt a driver's exam 3 times. This is not the case. Okay? I think this is not true. Okay? You can try as many times as you like, but this is okay. So let's say only 3. Now, the probability that someone passes at the first, second, or final attempts are this, and that respectively. What is the probability of an individual even passing the driver's exam? Okay, so how do you do this? Okay, so I would suggest try drawing a tree. Remember trees from the last time? Start off with, well, first attempt, what could happen? And then given what happened in your first attempt, draw another branch for the second attempt. What could happen? And then after the second attempt, draw a potential third attempt. What could happen? Based off what happened in the second attempt. Give it a try. See if you can draw a tree. So your tree will kind of look like this. Remember the tree for the product thing? Okay, that's what I'm talking about. But this tree is not exactly this. Right? There will be some things that you have to be careful when you draw this tree, right? Because not every previous situation will lead to a branching. I mean, I'll tell you, if you have already passed the exam, are you going to do it again? Are you insane? No, right? No one does that. So the tree has some branches that don't exist. So give it a try. Try drawing the tree and see if you can get the tree down, right? Okay. So are you seeing this as your tree? All right. Do you get something like this? Okay. So the first branch would be, well, we are told the probability of you passing the first time is 80%, which means 20% probability to fail. But given that you have failed, like that, the second attempt you might pass or still fail. So notice, be very, very careful. This is a thing to me. You must put the slash F1. Don't just say P2 like that. That's in P2 given F1 has happened. Notice there's no branching from here because as we said, once you pass, you're done. Maybe the only point that makes people confused is this one. How do you write the conditioning for this event? Do you see why it's parentheses F2 and F1? Because you know that the fact that you are here means you have failed twice. So don't write something like P3 slash F2 slash F1. That means nothing. You always slash on an event, but the event now is the intersection of these two because you know both of these must have happened for you to be failed. Okay, so put the numbers in. So what's the probability of you passing? This is easy. When the tree has been written down, and let me make a point here. If you do, there's a way to write this, and I'll tell you what it is. You pass by passing the first time, P1, or by passing the second time, given you failed the first time, times the probability that you failed the first time. So you see what's going on here. You take this number, that's passing on the first try, plus, well, passing on the second try. But passing on the second try happens when you fail first, and then you pass given you fail first. So I'm actually saying that if you don't know the technical way to write these things out, it's fine. The answer is what's important to you. But you can break it down carefully and write it down as a formula. PP1 plus P2 given F1 PF1 plus PP3 given F1 and F2 times F2 given F1 times P. That's what's going on. It's actually what's going on. So some trees are helpful, but sometimes trees promote sloppy understanding. But they are a useful way to get answers quickly. All right. So the likelihood of you passing eventually is pretty high, 99.9%, right? Because of all these provisions and also draw tree. Now, can you do the second part? Among those that passed, what's the percentage that failed at their first attempt? Do you understand the question? You are now conditioning on the pool of people that eventually pass. So what do we want? Condition on person has passed. What's the percentage that failed at their first? What you want is PF1 given person passes. Eventually. Right? Which actually, if you think about it, will this answer be close to basically P fail 1? Yes, because almost everyone passes in the end. See? So logically speaking, the answers will be quite close. All right. So what you should do here is something like this. Because what you want is, see, and as I said, so there is this answer turns out to be just under 0.2, which makes, I hope, intuitive sense. So you see, this is saying, what's the probability of you failing the first time, given that you're passed? Now that can happen in a bunch of ways. Maybe you did, see, you have to have failed the first time. And then maybe you passed the second time, your second attempt. Or you could be someone that failed both the first and second times, but then passed on the third time. It has to be either of these two, because you did pass at the end, and you divide by P pass. But the point is, the numbers are, again, get it off the tree, and I think it's pretty obvious. So I hope it's clear to you why this is close to 0.2. Because almost everyone passes. But they're not the same thing, right? They are not the same probability, actually, right? Okay, so we have this example. So I want to go back to our slides and finish up talking about some of these things. Okay, so we've discussed Bayes' theorem. Let me just highlight what it is. So Bayes' theorem says that you can turn a conditioning around. B given A is A given B, probability of B over probability of A. And then you can generalize it to any set of events that partition the central space. So HI given A, you can flip it around to be A given HI and so on. And that allows you to, if you break up your whole space into H1, H2, all the way to Hn, then this has to be the case. When A happens, A either happens with H1 or with H2 or with H3, and each of these can be written as a conditional product with that event. Okay, so nothing new here. It's a bit of revision. We talked about this the last time. So let's do some more examples. Okay. The completion of a highway construction may be delayed, okay, because of so the probabilities are 0.6 that there will be a storm, and 0.85 the construction job is completed if there is no storm, and 0.35 that the construction will be completed on time if there is a storm. Okay. What is the probability the creator will complete on time? Okay, so how do you get these numbers to mean? So first of all, was it clear to you that these two were conditional probability? Among those times where there was no storm, there's an 85% chance. But when there is a storm, there's only a 35% chance of being on time, something like that. And then we have this. So again, what do we want? We want the probability that something will be completed on time. And I'm just using A happens either with a storm or without. And just incorporate. So this is not difficult. Incorporate all the information in the right place. Again, you can draw a tree if you want, or you can use formulas. Let me ask you a question though. The way the information is given to you, when you draw the tree, I want to stress this. Whenever you draw a tree, you need to start with an event that you are going to condition on. Should I condition on project is completed on time, and then storm given project was completed, or should I start my first branch of the tree with storm, no storm? Do you know what I'm saying? When you draw a tree, you must pick an event to start the tree on. Do I start on project completion, or is the first branch based on storm status? Storm status. Why? Because yes, because the problem is primed that way. The problem gives you things in probabilities in terms of whether a storm is happening or not. So the direction of conditioning actually tells you when you draw a tree where to start. So don't start your tree by saying, okay, the project can be completed or not. It's not wrong, you know. It's just that that tree is not going to help you. That tree is you're going to end up with a tree that's unusable because there's too many things that you don't know. You have to align the tree's events according to the order in which they are given, all the information that you're given. So you need to know what kind of tree to draw. So if you draw one wrongly and you find that, hey, I don't know a bunch of these, you then draw another tree. Okay? Okay, let's go to another one. Let's see if you can do this one. All right, I'll give you a bit of time. A group of traffic violators consists of 45 men and 15 women. The men have probability 1/2 of being ticketed for crossing a red light. Women have a probability of 1/3 for the same offense. And suppose you choose someone at random, what's the probability the person will be ticketed for crossing a red light? And then determine the conditional probability that you chose a woman given that the person you chose was being ticketed for crossing the red light. Okay, so try to interpret the problem, see what's the direction of conditioning. You're going to use a tree, you can, but what kind of tree do you draw? So let me ask you, when you draw a tree, what is the event that you condition on, or the criterion? The way the information is aligned, what should be the first branch of the tree that you draw? Yes. That's right, sex, right? Because the way the information is presented is they tell you the sex of the they tell you that. So I didn't do it as a tree, but I actually would encourage you to draw a tree faster than that. So if you start off by C, woman is 15 out of 16, and then man is well, three quarters. So man, woman first. Then see ticketed given woman one third. Ticketed given man half. And we have what's the probability of, okay, first of all, what's the likelihood of being ticketed overall? So you need this. Why? Because eventually what you want is W given T. You want to know that among all those who are ticketed, what's the likelihood that person is a female, like that. So let me go over this again. First of all, gather the information that you have. Then write down actually what do you want. You actually want this. The tree is not aligned this way. But we don't worry because we have Bayes' theorem to help us to reverse things. You want W given T, but you know that Bayes says you can swap it to be T given W by doing this thing. And we want this. Why? Because the whole table of trees and the information is aligned this way. It's given in terms of sex first, as you rightly pointed out. And that's the answer. Does this answer make intuitive sense? Among those ticketed, probability that you're a woman is 2 out of 10. It does to me because, first of all, there were fewer women in the group. And then the likelihood of women being ticketed is lower. So this does not come as a surprise. So a lot of probability up to this point, I think, can be done by using common sense. I think most people who have a good sense of, I mean, if you ask a person on the street who has quite good number sense, they could figure out some of these probabilities pretty intuitive. I think this kind of question is the first one, where if you did not attend a probability class, unless you have really good intuition about sample spaces and restricting the sample size and all that, I don't think this is intuitive anymore. You need to learn Bayes' theorem. I don't think you can get this by using common sense. I mean, change my mind. If you think you can get this by common sense argument, let me know. I don't think it's so intuitive. All right. Some people are really smart. They're able to represent people with fractions and proportions. And they say, yeah, it's logical that now I'm only looking among these people. So it might still be possible, but it's just not so direct anymore. So you actually need to learn some probability to be able to do these kind of reverse conditioning problems like that. This is a very common thing that people want. All right, they give you information in a certain direction. You are supposed to turn it around. Okay, so let's go back to our slides. We finally visit the concept of independence. Now there's a few ways to look at independence. We'll go through all of them. Events A and B are independent if you can say that given B has happened, the probability that A happens is the probability of A happening. In other words, knowledge of B doesn't alter whether A happens or not, which is a very intuitive definition. Okay. This, of course, translates immediately to this quite common thing that we kind of know intuitively as well. The probability of A and B happening together, if they are independent, is the product of the two probabilities. Why? I've just told you, when two things are independent, then this must be true. So this, and in general, it is always true, A and B is A slash B, but A slash B has downgraded to A because of independence. So if you like, one good practice is when you do this equal sign, you can put the word independent on top. to remind you that this is only true because you have independence. If you don't, you cannot write that. So because of independence, we have this product thing. And in general, things get much easier. Remember that formula I gave you, A1, A2, AN, and then there's all the slash this, slash that. Yeah, if you know that all these events are independent, all that conditioning can be removed. Because telling me something about the process doesn't change anything about whether another event's going to happen because you have told me about it. Okay, so I would say this is a very often misused thing. You'll see this at even the highest levels in journal papers, and people assume independence. But what they should be using is a more general formula which has conditional probability. So they wonder why it's kind of like I'll give you an illustration. We in Malaysia, we have our version of an SAT exam, but it was much more involved and longer and standardized. The whole country did the same exam. Not like the SAT is the whole country as well. But then not everyone does the SAT. But everyone did this. Okay, but anyway, the point is, so sometimes people did like 10 subjects. And it was a very difficult thing to achieve that you get all 10, you end up with an A. You get 10 A's. And I would look at statistics, okay? And I calculated the probability that you get an A in any subject was pretty low. It's quite low. Maybe it was as low as like, I think 5% for any subject. 5% would get an A. Grade inflation has happened as well, but when I did this exam, there wasn't so much. So I used to think, wow, if one subject has only a 5% chance of getting an A, then if I did 10 subjects, how do I get all A's? So it's like 0.05, 0.05, 0.05. It's basically it's 0.05 to the 10, which is microscopic, which means what? No one would ever do that. It's so unlikely. But there were people who did that. So the flaw in my reasoning was I assumed that someone getting an A in one subject is independent of that same person getting an A in another subject. That's not true. If you are someone that already can get 7 subjects in A, you're pretty likely to get A's for the 8th and the 9th and the 10th. In other words, it was not independent. And so that was the flaw in my reasoning. But don't sue me. I was in high school. Yeah. I just thought, yeah, I did learn this in high school. And I said, oh, this doesn't make any sense to me because then no one will be achieving this. It's just too unlikely. It's not in other words, if you are already a student that's trying to do well like that, then you get more likely to get A's in other subjects as well. It's not independent. So that's the flaw in the reasoning. But you'll be surprised, this flaw in reasoning is displayed by many people. And then they wonder, how did this happen? It shouldn't have happened. Yeah, there was a flaw in your understanding of it. Okay, so the other thing is, if A and B are independent, so are A and B prime. These may not be so intuitive, but they are true. If you know A and B are independent, then A and not B are. Now, these are not that hard to prove. I will leave it for you to try. I think there's a homework problem like that also. You can try. Basically, just go back to, if I want to check the independence of A and B prime, I must show that P of A given B prime is also PA. Like that. That's how you check. And given that you know A and B are independent, how does that work out to prove that? You will find that you can show these things. This is important as well, because it is not obvious, that if A and B are independent, so are A and B prime. And if A and B are independent, so are A prime and B prime. So independence is quite far-reaching. So it's a very strong assumption, we say. All right. Okay, so let's do some more examples. So the probability of A is 0.4, probability of B is 0.7. So what's the probability that at least one mine is found in one of the states? Okay, how do you do this? So the probability of you finding at least one, I hope you realize, A union B, because it doesn't discount the probability of both. A union B is where you want to go. All right? because A union B includes the case of A and B. It does. Again, don't be confused. Sometimes people think that, oh, because I took it away, I'm not considering A intersection. No, it does. It's just that we double counted, so we take one of the take. All right? It does include A intersection inside it. And that's it. But we are told that A and B are independent, and that allows you to do this very big step. We can split this into a product property. Remember, this is only true because I've told you A and B are independent. Now, here's something I want to point out. On exams, sometimes the problem may not state that things are independent. And if things are told to you that they are not, if I don't say something is independent, don't assume it is. But there are problems, especially in life, where someone gives you an issue, a problem to solve. You do need to make some assumptions before you can solve the problem. Then tell me on the exam that, okay, if I assume independence, then this would be true. The context will tell you when that's acceptable. Okay? So basically, if I don't say, don't assume, but there are times when you solve a problem that you kind of have to assume independence. If not, the problem becomes too complicated. And this will be true on the homework and things like that. Okay? Don't worry too much. I've never had students kind of like make this mistake this by assuming it will be quite clear from the context whether something should be assumed to be independent. That's what I'm trying to say. All right. Okay, let's do another one. A and B are two independent events such that the probability of D happening, given that either A or B has happened, is 2/3. Right? Either A or B happening is 2/3. And then what else do we know? A given B is half, what is the probability of B? So first note by independence, we know that immediately we have a few things we can say. We know the probability of A has to be the same as this because you just told me A and B are independent. So this has to be true first of all. All right. What else do we know? We know that the probability of B given A union B by definition, it has to be this. Conditional probability means this, right? I want to ask you, how do I know that PB is on top? I mean, by definition, isn't this B intersection A union B? What is B intersection A union B? Anyone? What is B intersection A union B? Just B intersection A union B? Because you see, the definition of conditional probability is this intersect the other. What is B intersection A union B? Is B contained in A union B? Yes, and therefore B intersection A union B is just what? B intersection A union B has to be B, just B. See, A union B is a larger set, B is inside. So when you intersect a set that's completely contained in the larger set, it is that set. So B intersection A union B. So that gives you this. Then this is the theorem. Then again, using independence, you can eventually solve the problem. So this kind of thing, I won't say it's a very difficult problem, but sometimes you end up with, I don't know what equation to use. So the strategy is write down what you know and sort of like, I don't play around with things and see if, so basically the definitions are very, very important. You need to understand when you say that two things are independent, yeah, what are you saying? And if I know that, what does that enable me to write? And so you need to know definitions and theorems, of course, right? Okay. We will move on to another one. The probability that a blood sample shows cancerous cells, any blood sample, is 5%. 4 blood samples are tested and the samples are independent. This is very important because the problem would just become too difficult if there's some kind of dependent structure between the samples, all right? So in other words, they come from different people, all right? What is the probability that none shows any cancerous cells? Is this an easy question, right? So there's a 5% chance that a blood sample shows cancerous cell presence. So what is the probability that if I test 4 samples, none of them has any cancer cells? Anyone can tell me the answer? What work would you do to get this? You can assume independence from one blood sample to another. Anyone? What would this be? Yes. That's right. That's it. Okay, good. So nothing else, right? 0.95 to the 4 because that's the only way. Now, so you don't have to worry so much about all the wording, okay? We're just trying to, this is just formally saying that you want this and this and this and this. But we have learned that if you are allowed to assume independence of these events, then the complementary ones are also. When you don't need all this thing, okay? As long as you understand why it's 0.95 is the probability that anyone doesn't have anything, and you have a product because you're told okay, independent. Okay, let's do another one. What is the probability that exactly one has some cancer cells? Right. How would you do this? Remember, you're testing 4 blood samples. Exactly one has cancer cells. Then you describe what you would do to get the answer for this. Anyone want to try? Yes. Yes. Good. Not, yeah, to the 3. Okay. So 0.95 cubed and then 0.05. That gives you, but yes, there's one more thing you need to do. Does anyone? Yes. That's right. Multiply that by 4. I'll tell you why. Because, so what Maggie said, and actually what Sachi said. So it's two. First, you do this. But do you realize that when you say this, what are you saying? The first 3 were not, only the last 4. But you know, for one thing to happen, this could happen in 4 ways. Like that. So I'm slowly trying to sneak in something here. I have not formally introduced this, but I'll give you a chance. Does anyone know actually what probability distribution this comes from? This kind of answer. Does anyone know? This probability answer is so famous that it has a name. In other words, this probability structure, if you like, is a very, very famous one. Does anyone know what it's called? It has a name. I mean, probability questions come in all shapes and sizes. You can do it numerically, and we've done so many. This specific structure of taking that answer, one of them is to the power of 3, one of them is power of 1, multiplied by 4. This is pretty famous. It's so famous it has a name. Does anyone know what it's called? Yeah, I'll give you a hint. It starts with a B. Yes, good. This is a famous named probability structure called the binomial, which we will introduce formally. Not just yet, but that's why I slip it in now to introduce it. I wanted you to kind of intuitively get it yourself so that later when I teach it formally, it makes more sense. But this is the famous binomial distribution, actually. Let's do the last one. I think problem C says at least one shows cancer cells. Is there an easy way to do this problem? At least one shows cancer cells. So to me, when you see things like at least one and all that, the thing that first should come to mind is let's do this using a complementary argument. The only case you don't want is none of them has any. And so you have already found this answer from previously. Of course, there's the slow way as well, which is like, oh, at least one. Then, okay, well, one. You have just done the case where there's 1. And then you have to do 2. That would not be the smart way to do this. It's very slow. It's not wrong, but it's slower. The easier way is to use a complementary event, the opposite, which is what you don't want. Is this okay? So again, this is still binomial, by the way, but we will get there formally next time. Okay, I want you to try this one. An automobile owner is twice as likely to purchase collision coverage as opposed to disability coverage. Okay. The event that an automobile owner purchases collision coverage is independent of the event that the owner purchases disability coverage. All right. So you have some independence thing going on that should help you. The probability that an owner purchases both collision and disability is 0.15. What is the probability that an automobile owner purchases neither collision nor disability? Okay, I'll let you give it a think, right? Sit down. Try this problem first before I show you that. Right? Write down the things that you know. Immediately, you can use the independence hypothesis that you are told is true. So you can do it. Okay, so first of all, I hope you have collision coverage probability of buying is twice disability. So we have that. We have independence, so that leads you to the ability to save things. And we are told this value 15%. All right. And what else? You want this. Doesn't buy collision and doesn't buy disability, so you want. Okay, so how do you go about doing this one? So slowly work it out. First of all, you want this. Independence allows you to break this up like that. And because I told you, if D and C are independent, then all the primes and non-primes are also independent. So that allows you to do that. You know that this is this. One of the first things we learned is we proved it actually. You just expand and you can have it. Okay. But because we are told that D intersection C is this, and we know PC is 2PD, we get rid of PC here, and this is just so that we can find PD. So as I said, there's no algorithm for solving these things. You just have to list down what you know, what you want, based off the very few theorems that we have and any assumptions that they allow you to use them. Of course, you need to know the definitions of things. Okay, so I will ask you at this point to do an in-class problem. Here's what I want you to do. Can you construct a question like example 57? all three parts. But all I ask is think of a different scenario than cancer cell, right? I want you to dream up something else, but basically I want you to construct a binomial probability picture. Use a different number of different sample size, and but similar arguments. Just construct something that looks like example 57, but in a different scenario, different sample size. Maybe challenge yourself. Keep the sample size small, like 5 or 6 or something. Don't just say, don't do the exactly one. Maybe try challenging yourself. Exactly two. Awesome. So what's the probability that exactly two are something, right? See if you can dream up some kind of scenario, right? Like example 57. Okay, so if you can't finish it now, you can always drop it off later. All right. So let's move on to the last part. This is just some definition I need to tell you. I don't know if you know the exact definition of odds, but I'll tell you now. When people say the odds of E versus, well, the odds of E happening is defined as the probability of E divided by the probability of E not happening. Now, I am a person that doesn't think in terms of odds, but some people do it. I don't. It doesn't. I'm more a probability thing because you know why it's confusing. If you say the odds are 9 to 1, then you have to say it's 9/10, because 9/9 plus 1. So if you know if someone says the odds of E happening are A to B, then it's A/A plus B. It's the probability of E happening. So it doesn't come so intuitively to me, but that's okay. So let's just do some examples. Right, rolling a number less than 5, what are the odds of that happening? So on a fair die, there's 4 things less than 5. So you know the probability of you rolling a 5 or less, rolling 4 or less is 2/3. So the answer is basically 2/3 divided by 1/3. And so you have 2 to 1. I don't know. As I think about it more, maybe this is intuitive, but somehow I just don't think. Okay, tossing heads on a fair coin, that's pretty easy. It's 1 to 1. All right. This is pretty intuitive. Okay. Hmm. So again, this I don't know whether you realize if you assume independence of one birth to another, then you can use a binomial model. So that's it. But the binomial distribution is famous for a reason. It gets a lot of application. So if you assume uh, that uh, subsequent births are all independent, then you can make this assumption. I don't think that's necessarily true, uh, but it's a simplifying assumption. Because there are people that tend to have in multiple pregnancies, children of one sex. I noticed that, but I'm sure people have studied this all over the place. I don't know if there's any evidence that independence cannot be assumed, but I'm going to assume independence here. So the probability of all 4 births resulting in males is 1 in 16. And so the odds against that is 15 to 1. So what's the interpretation of that? Well, it just means that in a whole bunch of families that have 4 births, only 1 in 16 basically in the long run will be all 4 boys. Similarly, all 4 girls the same probability as well because you assume this is starting. Okay, so that's so the only thing to take note is when you say odds, it's like odds for or against. If you say against, then it's the opposite effect, right? You can turn it around. Okay. What are the odds in favor of getting at least 2 heads if a fair coin is tossed 3 times? So this is just a twist. So first of all, you need to find the probability of the event of interest. Getting 2 heads or more If you toss a coin 3 times, is half. So the odds of that is still 1 to 1. As I said, you must determine which event is favored. Which event are you talking about? Find the probability of the event and do 1 minus this over 1 minus the probability of the other. I mean, I don't want to spend too much time. I'm just defining what odds are in case someone doesn't know. Right? I do know some of you like playing card games, and every time I teach a probability class, I have at least one student that is an avid card game player, and I know your experience with these things far outweighs mine because I'm not a game player of any game, right? So I don't do that. Okay, so let's go on now to chapter 5, and we'll see how far we get. Okay, so chapter 5 is our introduction to what we call random variables. It's very, very important, and it's not hard. It's actually, it's something very, very intuitive and natural, especially at a less rigorous level. If you did a very rigorous probability theory class, uh, the definition of a random variable is not very intuitive. It's what we call a measurable function and all that, which we will not get into, right? We will just do it very, very intuitively. A random variable is a mapping from the sample space to the real number. So in other words, it ships things from the sample space, which is pretty arbitrarily, or you can have non-numbers in a sample space. It could be people, it could be things, but you assign some kind of number to it. Now the thing about random variables is that there are 3 kinds. There are continuous random variables, there are discrete, and then there are those that are both. Okay, this is by far the most mysterious one, and we will hardly talk about this just a little bit because you need a lot of measure theory machinery to really make these things concrete and all that. You can go knock yourself out and go and read about these things. You can check out the Cantor set, the Devil's Staircase, and all that. There are all kinds of wonderful things you can go blow your mind, right? But we will not do that in this class. Okay, so to keep things simple, for the moment, we just consider discrete random variables. Okay. So let me give you an example. Discrete random variable. Oh, first, okay, sorry. Before doing that, let's classify. A coin is tossed 10 times, and the random variable is the number of tails rotated. I hope you have this as a discrete random variable because the set of values that the random variable can take are basically what? You toss a coin 10 times. How many tails did you get? Anything from 0 to 10, that's a set that is finite. Therefore, it's a discrete random variable. Okay? A light bulb is burned until it burns out. The random variable is a lifetime. I hope you realize things like lifetime exist on a continuum. So that would be an example of a continuous random variable. Lifetime is measured on a continuum. Now, this is I put this example there to show you an example of this kind of weird kind of random variables that display both these kinds of random variables display both the features of discrete and also continuous nature. So what do I mean by this? First of all, what's my sample space? My sample space is any number in 0 and 1. 0 to 1, sorry. Any number from the interval 0 to 1. And I assign the value 1 minus s if the value that I picked was between 0 and a half. And then it's half if the value that I picked was half to 1. So what's strange about this is it's both, this section of it is discrete because it's just one number. But this section is continuous. So it plays both roles. So it's both. All right. So it's what we call a mixed random variable because the key to note is look at the range of values that it can take. Right? Look at the range. If the range are is a finite set, usually integers, then it's a discrete random variable. V is continuous in that zone, but then it becomes discrete on another zone. So it's it's a hybrid, right? This is a very easy problem. If you toss a coin 3 times, well, these are the things that can happen. This is a sample space. X is a random variable. Why? Because it's going to assign things values to the things in the sample space. So if X is measuring the number of hits in 3 tosses, find the range of X. I hope it's obvious the range is 0, 1, 2, 3. Right? Range is the set of values that a function takes. So the range of X is 0, 1, 2, 3, and that means X is a discrete random variable because any finite set is a discrete random variable. Any finite set results in a random variable that is discrete, right? Okay. Example 64 may be something a little bit nicer to talk about. And you can give it a try, all right? Okay, let me ask you to do this. You can discuss with your friends if you want. So now you roll 2 rolls of a fair four-sided die. So the die is like a pyramid. Okay. I kept it at 4 because I didn't want you to do too many calculations. So you have a four-sided die. So you can, and then X is the random variable equal to the maximum of the 2 rolls. So I want to give it a slight twist. This is just whether you know how to list down. Do you agree, first of all, that these are the only values X can take? But now can you work out the probability that the maximum of the two is? What needs to happen? Maybe you can tell me. What needs to happen in the 2 rolls so that the maximum is 1? What did you need to see so that the maximum of the two is 1? Both times you got 1. Okay? So note that. Then what did you need to see so that the maximum is 2? Okay, so this one is going to be, there's a bunch of things that could have happened that yielded a maximum of 2 like that. So here's what I suggest. I hope you realize some of these are more complicated than others, right? Because they involve more cases. So be smart about it. You know that the probability has to sum to 1. So do as easy of a case as possible, leaving one of the complicated cases uncalculated because you know it has to be 1 minus the other. Did you see what I'm trying to say? Some of these are easy. This case and this case are easy. Just do one of these. And you can actually pick the easier of the, I think it's symmetry. So basically do 3, do the 2 ends are the easier ones, and do one of the complicated ones, and then leave out the other because you know these probabilities have to something. All right. Okay, so first of all, we have argued that for you to get a maximum of 1, the only way this happens is both will 1. But what's the probability of that happening? So the 2 rows you're going to assume are, what have you tacitly assumed about the 2 rows? The 2 rows are independent. You kind of have to. Because you don't know anything else about the die, so you're going to have to assume that. So is it clear that the probability of any of these things happening is an equally likely sample space? Because there's no bias to anything. You are equally likely to see any of these things, which means there's a probability of 1 in 16 for any of them. And this is exactly one case. So the case for getting a maximum of 1, the probability is clearly 1 over 6. And then for the maximum to be 4, a whole bunch of ways this could happen. And because all these, as long as one of them is 4, that will fulfill the criterion already. So just count cases. The important thing to note here is the definition of the random variable. That's quite important. Sometimes students have a bit of difficulty knowing what are you measuring. So in this case, you're looking at the maximum of 2 rows, assuming independence, and the die is fair. All 16 eventualities are equal probability, so it's just basically becoming adding cases up. And if you don't want to do all the cases, you know that eventually they have to suffer. All right. Mm. 2 apples are selected at random and removed in succession without replacement. So the bag has 5 golden and 3 red. List the elements of the sample space and the corresponding probabilities and the corresponding values of the random variable x, where what does x measure? X is the number which are golden. I will let you think about this one first. Okay. X measures the number of golden apples selected. First of all, the sample space can be as complicated or not as you like. I don't know whether you went the route of saying, oh, it's the first golden apple or the second one or the fifth one or what. You can do that, but that gives a level of granularity which is not required, but it's also correct. Okay? This is just saying the apples are indistinguishable. If you make them distinguishable, it's not wrong, but it just makes your sample space a more complicated affair. So, what is the probability that you didn't pick any that were golden at all? So I hope it's obvious. There are three red. So there's a chance that the first one you take out is red is 3 out of 3. But because you don't put things back, the next one has 2 out of 7. I hope that's intuitive to you why these 2 are like that. Now, notice this is not first is golden, first is red, second is also red. It's not R1, it's not PR1 times PR2. It's PR1 times PR2 given R1. Again, I don't know whether how you were taught. Too often, people are very tempted to, okay, basically this means what? Both apples that were picked were red. And that means the first apple picked is red, is R1, and the second apple picked is red, is R2. So you do want R1 and R2. But what I'm trying to tell you is notationally, this is not PR1 times PR2. So sometimes we are tempted to write that because we know there's a product involved, but it is not PR1, PR2. The correct notation is PR1, and this is PR2 given R1. Because isn't that true? If I tell you that there's one red apple that has been removed,
only then you can say that the probability that the second one I take out is red is 2 out of 7. See? PR2 alone with no conditioning actually is a very weird question. It means, what is the probability that the second apple I took out was red? So do you need to consider, if you wanted to answer that question, would you need to consider, oh, if the second one was red, maybe the first was also red, or the first was golden. Do you see what the point I'm trying to make? PR2 is not the same as R2 given R1. R2 given R1 is more intuitive, actually. If I know that the first apple is already red, then the second being red is a much easier probability to think about conceptually. Okay? I really want to make this point because this is a consequence of how we learned this in high school, and my teacher did not do a good job in this sense. They taught us how to get the answer, but there are a lot of notational things that were just thrown by the wayside. They would even write, things like R1 and then R2, it's R2 given R1. Because writing strange things like that, wrong things like that, gives the impression that R1 and R2 are events that are independent. Not independent. The probability that you get a red second apple is not independent of the status of the first one, because there's a finite number of apples in the bag. What you take out first is going to affect the probability of the second. So let's be careful. Then we can extend it to what's the probability of one golden. Okay, if one is golden, it could be the first one that was red or the second one, first one that was golden or second one that was golden, but exactly right. All the conditional arguments apply because it just means, or maybe it was R2 and gold one, or it was R1 and gold two. But basically, to break up a intersection, you use conditioning and you condition on the first event. What did you pick out first? Knowing that, what's the probability that the second one fulfills any criteria that you want? Okay, so you can slowly fill in the table and get all the answers like that. And I hope it's obvious there's only 3 possible values in the range of x, 0, 1, or 2. Because you're only drawing out 2, all right? Okay. Let x be a random variable whose distribution is given below. So you see the range of x here is 0, 10, 20, 50, 100. So this is a discrete random variable. Because the number of values x can take is finite. I give you the probabilities assigned to each of them. So this is answered in exactly the same way that you did for any other event. X less than 50, opposite event is greater equal to 50. So you just add up the probability of those two cases. So in other words, these are like events. When you ask for the probability of something, you're actually saying what's the probability of which things in the sample space yield an X value that are less than 50. All right? So that's it. Then you toss a coin repeatedly until you get heads. Let x be the random variable representing the number of times the coin flips until the first head appears. Do you agree that the probability that I need to toss n times before I see my first head is given by this one? If you assume all tosses are independent. First of all, do you agree with this? Why is there n minus 1 here? Because tail, 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 and the last one is a head. Then you stop. Because what does x measure? X is how many times must you do something until something happens, including that time. All right. I purposely put this example here because, first of all, can you answer me this? Is x a discrete random variable? It is because its range is countable, but it's not finite. All right. So listen carefully to what I say. Any random variable whose range is finite is discrete. But you can have discrete random variables whose ranges come from sets that are infinite, but those sets need to be countable. Because could you toss a coin and never get a hit? In theory, yes. So it could go on forever. So the range of x here is, well, it starts from 1. Maybe you toss once and you've got to get immediately. 1, 2, 3, 4, 5, never ends. So this is what we call a countable range, but it's not finite. So it's not that discrete random variables must always have finite ranges. Anything with a finite range is discrete, but the other way around may not be true, okay? So a discrete random variable, the definition is if the range is countable, which this one is. Now, this is, again, a very famous probability model. It has a name. Does anyone know what it's called? We've introduced the binomial today. This has a name as well. Has anyone heard of this one? That you know what name this distribution that follows this probability structure is called? Does anyone know? It starts with a G.
Geometric.
This is the geometric probability model. And for good reason, because you will end up with a geometric sum to infinity here. But all that in good time, all right? Last example, then we'll call it quits for today. The number of injury claims per month follows that distribution. Okay? And determine the probability of at least one claim during a month, given that there have been at most 4 during that month. What? Okay. So how do we do this problem? What do you even want? You want the probability of there being at least one claim, given that that is a month that has no more than 4. The given there is the biggest giveaway that this is a conditional probability. All your old definitions are conditional probability. Fine. If I want to know the probability of this event happening, given this event has happened, what I need to do, I intersect the 2 of them, and you divide by this probability. Simple. So what is the intersection of n greater than 1 and n less than 4? Anyone? If I say, I want to see what is this and this, is it clear what this is actually? N is both 1 or more and 4 or less. So what am I saying? N must be between 1 and 4, inclusive. That's right. And so that's exactly what you need to do. So this is essentially saying N is between 1 and 4. And this just becomes, we'll use this formula to compute this, because N being between 1 and 4 means what? 1, 2, 3, or 4. And then you divide by the probability of, you just add one extra case. This includes the case of 0, because N could be 0. So give this a think. I know I went through this a little bit quickly, but I don't think it's that difficult. Just what I'm trying to say in this example is that the definition of conditional probability is the same. Just interpret it in terms of random variables. All right. So have a good weekend, and I think you'll be in good shape to finish your homework. But I think I sent it to next Tuesday or whatever that was. So